So hi again. I'll now talk about a completely different topic. So we'll move on to a communication issue, and we'll see how we can apply Xampling ideas to the application of cognitive radio, which Janina started talking about in her talk. So we all know this image, which is the FCC frequency allocation map. And we see that basically all the frequencies that are allocated to different users by governmental institutions. So basically they're all already owned, and the spectrum is too crowded, and if a new user wants to come and use and buy a spectral band to use it for transmission, it's really hard to find a free band. So these are the bad news. The good news is that the spectrum is underutilized. So we have many different studies that show that at a given place in a given time, not all the primary users are using their signal and are transmitting concurrently. So these are studies from Chicago, from the UK, from London, and they all show that most of the spectrum is not actually used. So the idea is, the question is, can we exploit these temporary spectral holes for transmissions in an opportunistic way? So this is basically the motivation behind cognitive radio, what we want to do here is to use these spectral holes, these white bands that we are not using. So what we have to do is to sense the whole spectrum, and the wider the better, because the wider the more chances we have to find a white band. And as long as you are transmitting, you have to continue to monitor the spectrum, because you don't want to disturb a primary user that started to want to use its band. So what we have to do is that we have to sense a wide band of spectrum. We have to do that in real time to be very reliable, because you don't want to disturb the primary user that bought this band. And we obviously want to do that in minimal resources. So sampling this kind of signal at the Nyquist rate is not an option, because the signal are very wideband. So the question is, how can we do that? How can we efficiently perform detection on such wideband signal? So what we are seeing, the signal model that we have is the multiple model that Janina talked about. So we have several narrowband signal spread over a wide spectrum, and we don't know where they are. And so we don't want to sample this signal at its Nyquist rate. So what we want to do is to have this analog front end as a beginning that aliases our signal. We'll sample our signal at a sub-Nyquist rate and reconstruct it digitally. And as Janina said before, the minimal sampling rate for this kind of scheme is twice the Landau rate, which is twice the actual occupancy here. So if we have n bands, each with a bandwidth of b, the minimal sampling rate that we have here is 2nb. So this is theoretical. So how do we do that in practice? So in the group, we've developed two specific sampling schemes. So the first one is multi-coset sampling, also known as interleaved sampling, where we basically divide the Nyquist grid into different cosets, the n cosets. And from this coset, we only take m samples out of n. So we only keep those samples. And obviously, the overall sampling rate here is m over nt. So to implement this multi-coset sampling, we can use different channel, where each channel has a different time shift and a sampler at a low rate. So this approach has several practical drawbacks. One of them is maintaining accurate delays between the channels, which can be challenging. The second, and maybe the most important one, is the analog bandwidth. So our low rate sample have anti-aliasing filter built in. So when we sample at a low rate, we actually have a filter low pass filtering our signal. So we don't sample the actual signal that we have here, the actual wideband signal. And the third drawback is that the number of channels here has to be twice the number of bands that we have in our signal, and this can't be reduced in any way. So facing these practical issues, we moved on to a second scheme, the MWT that we are going to see today, the modulated wideband converter. So what basically we do here, we look at several channels. In each channel, we multiply, we mix our signal with the periodic function. We then low pass the result and sample at a low rate. And this is what we obtain in all the different channels. And also here, the overall sampling rate is m over nt. So here we don't have the practical drawbacks that we had before in multi-cassette, especially the number of channels here can be collapsed to only one channel. So what we have to do is only to take a wider low-pass filter. And what we see here, what we sample basically is equivalent to what we would have sampled in different channels. So instead of having several channels, we can have only one. So we overcome these practical drawbacks, and what we see here is that what do we do with the sample? So this is what I sample, either in multi-cassette sampling or in the MWC, no matter how many channels. And this is my samples in the frequency domain. And what I can say is that I can write these samples as a linear combination of the slices of my signal. So if I take my multi-band signal and I cut it into slices, put them into a vector, this is what I get. So basically, this is what I want to recover, because if I recover x, I recover my signal. Oops. And if I recover x, I recover my signal. And I want basically to recover x from z. So the matrix A here, which denotes the linear combination, is a known matrix. It depends in multi-cassette sampling on the different delays in the channel, or in the MWC on the Fourier coefficient of the sampling sequence. But what is important is that it's known, and what I want to do is to recover x, which is unknown, for z from z that are my samples. And obviously, if I sample below the Nyquist rate, A is a fat matrix because I have less equations than number of entries in my vector x. And to recover x from z, as we said before, we use compressed sensing technique. So what's the problem with what we have now in the context of cognitive radio? So with our system now, we have two main drawbacks. The first one is what we're doing is overkill, because we recover the signal when we actually only need to recover its support. So the question is, if we only want to recover the support, can we further reduce the sampling rate? The second issue is the robustness to noise, and we had a question about that before. And what we do here, we purposely alias the signal all over the spectrum. So when you alias the signal on purpose, you also alias the noise, and you lose in robustness to noise. So what we're going to show in this talk is that if we recover the statistics and not the signal, we can reduce the rate, and we can also and we are also more robust to noise, especially when we're going to use cyclostation detection, and we're going to talk about that in a few minutes. At the end of the talk, we're going to talk about two more extensions. So one is collaborative spectrum sensing, when I have several cognitive radio collaborating together to recover the support, and joint direction of arrival and spectrum sensing, when I'm interested not only in the support, but also in the angle my signal is arriving from. So let's start with a small outline, and then we'll move on to the first part of the talk. So in the first part, we're going to talk about Nyquist sampling for statistic recovery, and we're going to see that we don't have to assume any structure in the signal in order to recover the statistics from Nyquist sample. In the second part, we're going to go back to assuming structure, and we're going to Nyquist our signal exploiting its sparsity, both in frequency and in the space. So let's start with the first part, where our goal is to recover the statistic of the signal. So here we're sampling our signal, but we don't want to recover it. We want to do something else. We have a different task, and our task at hand here is statistic recovery. So what is done so far today is to take our signal, to sample it at the Nyquist rate, to reconstruct the signal, and from the signal reconstructed, we estimate the statistics. So the compression is done in the digital part from our samples to the statistics that we compute. What we want to do is to move the compression earlier. We don't want to sample our signal at this high rate to throw out the samples that we don't need and compress afterwards. We want to compress before. So we'll have analog preprocessing doing the compression. We're going to sample our signal at a low rate and recover the statistics directly from the low rate sample. So the question is, can we actually do that? Can we actually sample below the Nyquist rate when our goal is not to reconstruct the signal, but the statistic without assuming any sparsity or any structure in the signal? So what we're going to focus on is power spectrum reconstruction. Power spectrum or covariance is the same. And actually, in many applications, we don't need the signal itself. We need only the covariance. And cognitive radio is one example of such application. And the question is, if I want to recover only the covariance, what is the minimal rate that I need to sample my signal? And we only assume, so I said we're not assuming in structure. The only thing that we are going to assume is that we have a wide sense stationary ergodic signal. And this is the only thing that we want to assume. And we'll look at two cases. The first case is a general band limited signal. And the second case is if we want to go further and indeed assume a certain structure, we're going to go back to our sparse multiband signal and see if we can do better with this further assumption. And we'll see that in both cases, the sampling rate will be much lower than Nyquist or Lambda, which are the rates that we need if we want to recover the actual signal. So we'll take a little detour from all this cognitive radio and MWC to go more deeply into the math and answer this question, which can be a completely theoretical separate question about what is basically the sampling rate to recover only the covariance. So we have a wide sense stationary signal, and what we want to recover is not X itself, it's its covariance. So what we want to design is a stable sampling set for the covariance Rx. So this question has been looked over in the past half century. So first, people are looked at random sampling and especially Poisson sampling. But if we want to do something practical, we need deterministic sampling. And specific schemes have been looked at, especially coprime and multi-cassette sampling. But what we want to do is to develop something general, and we want to understand what are the conditions on the sampling set in order to recover the covariance. So what we need to define before is what is sampling rate. So if I sample uniformly, this is easy. The sampling rate is basically the spacing between, 1 over the spacing between my samples. So if I have a spacing of t between my samples, the sampling rate is 1 over t. If I sample non-uniformly, and this is what we're going to do, there is no such thing as spacing between samples. So what we're defining here is the lower Berlin density, which is something like an average sampling rate. So the lower Berlin density basically takes the number of dots of samples that we have in a certain interval and divided by the length of the interval, which is the average density of our sampling. And if we go back, for example, to uniform sampling, we see that the lower Berlin density of a uniform sampling set is 1 over t, which gets us back to the sampling rate. So the lower Berlin density will be our sampling rate for non-uniform sampling. And we know that a set is stable if its lower Berlin density is above the Nyquist rate. This is true when I want to recover the signal. So I want to get a similar equation when I want to recover the covariance. So the question is, what is the lower Berlin density on the sampling set if I want to recover the covariance? And what is very important to understand here is that I sample my signal. So the sampling set, the times that I sample is times that I sample x. What I want to recover is the covariance. And what is interesting is that the covariance only depends on the time lags. It only depends on the differences between 2 times. And what can happen is that even if I have a small sampling set, the difference set, when I look at the timeline lags, can be a lot bigger. And this is what we're going to exploit. So what we're saying is that, and this is the rate that Yonina didn't want to tell us before to not spoil the surprise, is that what we're saying, we can recover the covariance of any signal with a sampling set of burying density 0. That means that we can have a sampling rate going to 0 and be able to recover any covariance. So what's happening here? What we're saying is that even if we take a sampling set with burying density 0, which means average sampling rate 0, so the difference set can be a lot more dense. And what's important to us is the density of the difference set and not the density of the sampling set, because we're interested in the covariance. So if we have enough differences, so the difference set is bigger than the sampling set, and if the density of my original set, of my sampling set, is going to 0 but not too fast, it's going to 0 but slower than the square root, then I can have a difference set with density going to infinity. And if the density goes to infinity, this is higher than any Nyquist rate of the covariance. And this is what the theorem here is saying. So let's take two small examples about such sampling sets. So if we look at the Cantor-Tenore set, so basically you take a segment 0 to 1 and you repeatedly cut the open middle segment, the open middle third. So what you get at the end is a sampling set with density 0, but the difference set here will be with density infinity. So this is a good set for us. Bad set for us is, for example, uniform sampling, because in uniform sampling, the sampling set and the difference set are the same. So if the lower Berlin density of the sampling set goes to 0 when t goes to infinity, then the lower burying density of the difference set goes also to 0, because I don't have enough distinct differences, because when I sample uniformly, all my differences end up to be the same. So this is not a good set for us. So we saw that in general, when the average sampling rate of my samples in the signal goes to 0, I can recover any covariance. But this is general, and the question is now, can we analyze practical sampling set? Can we analyze our Berlin density and see what happens in practice if we want to build a sampler? So let's go back to multi-coset sampling. And in multi-coset sampling, we saw that we have m channels, each sampling at the rate nt. So here, the average sampling rate, or the burying density, is m over nt. So the question is, when I'm using this specific sampler, what is the minimal sampling rate in order to recover the covariance? And the answer is that the lower Berlin density of the difference set in this case goes something like the square of the lower Berlin density of the original set, the sampling set, if we take care that all of our difference in the cosets are different. And the conclusion is that for signal recovery, I need my sampling rate to be greater than Nyquist, which means that m should be greater than n. If I only want to recover the covariance thanks to this power of 2 here, I only need this square root. So I only need m to be greater than the square root of n. So without assuming any structure on the signal, I gain the factor of the square root. Now, if I go back and assume that I have this sparse multiband signal that we saw in cognitive radio, so in this case, we know that to reconstruct the signal, we need the minimal rate to be greater than twice the actual occupancy, twice the lambda rate. And here again, if we want only to recover the covariance, we only need square root of this lambda rate. So to summarize up until now, what we saw is that if we need to recover not the signal, but we can recover the statistics, we can reduce the rate more and more. The second issue that we had with our system is robustness to noise. We all know that energy detection fails in low SNR regime. So here we see Nyquist rate, here we see results at some Nyquist rate. So you see here a shift of 10 dBs. So the phenomenon here is even worse when we sample at some Nyquist rate because of the aliasing. So the question is, how can we increase the robustness to noise of our detection? And what we're going to do, we're going to exploit a certain property that have communication signals that are not shared by stationary noise. And this property is called cyclostationarity. And this is a property of processes that have statistic periodic that vary periodically with time. And what is interesting with these processes is that they have a characteristic function called the cyclic spectrum, which can be viewed as an extension of the known power spectrum. So this is a two-dimensional extension, and we have in the cyclic spectrum peaks at certain locations. The locations are called cyclic frequencies, and they depend on the carriers and the bandwidth. So here we see the cyclic spectrum of different modulation family. And basically what we're going to do is that we're going to take our Nyquist samples from the MWC, for example. We're going to reconstruct the cyclic spectrum. And when we have this image, we're going to estimate the carriers and the bandwidth from the peaks here that we're going to detect. So we reconstruct not the signal, but the cyclic spectrum, which is one of a statistic function. And we recover the carriers and the bandwidth. So the cyclic spectrum is basically measured the correlation between two frequency shifted versions of our signal, and this is what we want to compute. So if you take alpha equals 0, you get the power spectrum, and we want to compute this for all alpha. And if we remember, this is what we have. This is our samples, and they are equal to